Quantum vacuum catastrophe. What is nothing? For centuries, we imagined it as a perfect void, an absolute emptiness. A silent, black, featureless stage upon which the drama of the cosmos unfolds. But what if that stage is not empty at all? What if the very fabric of reality, the space between stars, between atoms, between you and the screen you're watching, is the most chaotic, energetic, and misunderstood thing in the entire universe? Modern physics has stumbled upon a terrifying secret hidden in plain sight. A mistake so profound, it has been called the single greatest failure of a physical theory in history. It's a discrepancy not of a few percent, or a factor of 2, or even a million. It's a miscalculation that spans 120 orders of magnitude. This isn't just a rounding error, it's a cosmic catastrophe that proves our most fundamental understanding of empty space is completely and utterly wrong. To understand this colossal blunder, we have to journey to the bizarre world of quantum mechanics. In the early 20th century, our view of reality was shattered. We discovered that at the smallest scales, the universe doesn't operate on the predictable, clockwork rules of classical physics. Instead, it's governed by probability, uncertainty, and a strange set of laws that defy all common sense. One of the cornerstones of this new reality is quantum field theory, or QFT. QFT tells us that the universe isn't made of tiny billiard ball particles. Instead, it's filled with invisible, intangible fields. There's an electron field, a photon field, a Higgs field, a field for every fundamental particle we know. What we perceive as a particle, like an electron, is just a localized vibration, a tiny ripple in its corresponding field. Think of it like a vast, invisible ocean. A ripple on the surface of this ocean is a particle. This is where our notion of empty space begins to crumble. What happens when you remove all the particles, all the ripples from this ocean? You might think you're left with nothing, a calm, flat, zero energy state. But the quantum world is never calm. Heisenberg's uncertainty principle forbids it. The principle states that you can never simultaneously know certain pairs of properties, like a particle's exact position and its exact momentum. A similar uncertainty exists for energy and time. This means that even in a perfect vacuum, the energy of a quantum field can never be exactly zero. It must constantly fluctuate. This residual, rock-bottom energy that can never be removed is called the zero-point energy. Because of this zero-point energy, the vacuum of space is not a tranquil void. It is a seething, frothing, chaotic mess. It's a seething cauldron of quantum activity, where pairs of virtual particles and their antimatter counterparts, electrons and positrons, quarks and antiquarks, are constantly popping into existence, borrowing a tiny bit of energy from the vacuum, interacting, and then annihilating each other in a flash, all in a time frame so incomprehensibly short that they cannot be directly observed. They are the ghosts in the machine of reality. While they are fleeting, their collective effect is very real. They exert a pressure, they contain energy. This is the energy of nothing, the energy of nothing. So, physicists decided to calculate it. Using the well-tested framework of quantum field theory, they set out to sum up the zero-point energies of all the known quantum fields at every point in space. The calculation is complex, but the idea is straightforward. Add up all the tiny, ghostly contributions from all the virtual particles. When they did this, the number they got was staggering. It was, to put it mildly, the biggest number in the history of science. The predicted energy density of the vacuum was enormous, an almost infinite well of power contained in every cubic centimeter of space. In fact, the energy predicted to be in a volume the size of a coffee cup would be enough to boil all the oceans on Earth instantly. If this calculation were correct, the immense energy of the vacuum would exert a colossal gravitational force. Space-time itself would be violently curved, and the universe would have expanded so rapidly that galaxies, stars, and planets would never have had a chance to form. It would have ripped itself apart in the first fraction of a second of its existence. But that's not what we see. We live in a relatively calm, stable, and very large universe. This brings us to the other side of the story, cosmology and Einstein's theory of general relativity. For decades, astronomers have been observing the universe on its grandest scales. And in 1998, they made a shocking discovery. By observing distant supernova, they found that the expansion of the universe is not slowing down due to gravity, as everyone expected. It's accelerating. Something is pushing space apart, acting like a sort of anti-gravity. Scientists gave this mysterious force a name: dark energy. According to our best cosmological models, this dark energy appears to be a small positive energy density inherent to the fabric of space-time itself, a cosmological constant. And here is the heart of the catastrophe. We now have two completely different pictures of vacuum energy. On one hand, quantum field theory predicts a vacuum energy density that is astronomically, incomprehensibly huge. On the other hand, cosmological observations of dark energy show us that the actual energy density of the vacuum is incredibly, unbelievably tiny. It's not zero, but it's close. When you compare the theoretical prediction with the observed reality, the numbers don't just miss. They disagree by a factor of 1 followed by 120 zeros. Let's try to grasp the scale of this error. It's like measuring the length of the entire observable universe and being off by the width of a single human hair. No, that's not even close.
It's like measuring the diameter of the Milky Way galaxy and being off by the size of a single bacterium. Even that fails to capture the absurdity. There is no analogy in human experience that can adequately describe the magnitude of this failure. It is, without a doubt, the most profound and embarrassing disagreement between theory and experiment in all of science. This is the vacuum catastrophe, and it tells us that our two great pillars of modern physics, general relativity and quantum mechanics, are fundamentally incompatible. It's a glaring signpost pointing to a deep crack in our understanding of reality. A mystery that begins with the simple question of what it means for space to be empty.
Implications and solutions. The 120-digit error is more than just a physicist's nightmare. It's a cosmic riddle that strikes at the heart of our most cherished theories. This isn't a problem we can just sweep under the rug. It's a fundamental contradiction that sits at the crossroads of the very large and the very small, and its implications ripple through all of modern cosmology and particle physics. The most immediate consequence is our understanding of dark energy. When astronomers discovered that the universe's expansion was accelerating, the most natural explanation was the energy of the vacuum, the cosmological constant that Einstein himself had proposed and later called his biggest blunder. It seemed like a perfect fit, a constant, intrinsic energy of space pushing everything apart. The vacuum catastrophe turns this elegant solution into a source of immense frustration. The priv energy seems right, but the N is catastrophically wrong. It's like ordering a cup of coffee and being served an entire ocean. Why is the observed value of dark energy so ridiculously small compared to the theoretical prediction? Is it just a cosmic coincidence? Or is vacuum energy dark energy after all, and the similarity is a red herring?
This question has stalled progress in cosmology for decades. This crisis forces us to confront the schism between our two best descriptions of the universe. General relativity, Einstein's masterpiece, governs gravity and the cosmos at large scales. Quantum field theory governs the three other fundamental forces and the universe at the smallest scales. Both theories have been tested to incredible precision in their own domains. But where they meet, in the quantum nature of space-time itself, they break down spectacularly. The vacuum catastrophe is Exhibit A. It proves that we are missing a crucial piece of the puzzle, a more fundamental theory that can unite these two frameworks. This hypothetical unified theory, often called a theory of everything, must, as one of its primary functions, solve the vacuum energy problem. It must explain why the quantum jitters of the universe don't tear it to shreds. Finding this theory is the holy grail of modern physics, and the 120-digit error is one of the biggest clues and biggest obstacles on that quest. So, how do we fix this? Physicists have thrown some of their most brilliant and exotic ideas at the problem, each with its own set of promises and pitfalls. One of the most elegant early contenders was a concept called supersymmetry, or SUSY. Supersymmetry proposes a deep underlying symmetry in nature. For every known fundamental particle, there exists a heavier superpartner particle. For every fermion, there's a corresponding boson, and for every boson, there's a corresponding fermion. The beauty of this idea, in relation to our problem, is that fermions and bosons contribute to the vacuum energy with opposite signs. In a perfectly supersymmetry universe, the positive energy from all the bosons would be perfectly canceled out by the negative energy from all the fermions. The result would be a vacuum energy of exactly zero. This would almost solve the problem, leaving only the small observed value of dark energy to be explained by some other mechanism. The problem? If supersymmetry were a perfect symmetry, we would have discovered these superpartner particles by now. Experiments at the Large Hadron Collider have found no evidence for them, which means if SUSY exists, it must be a broken symmetry, and the superpartners must be much heavier than their standard model counterparts. This breaking of the symmetry ruins the perfect cancellation, and we're left right back where we started with a huge, unexplained vacuum energy. Another approach comes from the mind-bending world of string theory. String theory posits that fundamental particles are not points, but tiny, vibrating strings of energy. For the theory's mathematics to work, it requires the existence of extra spatial dimensions beyond the three we experience. These extra dimensions are thought to be curled up into complex shapes on an infinitesimally small scale. According to the theory, there isn't just one way for these dimensions to be curled up. There are a staggering number of possibilities, perhaps 10 to the power of 500 or more. Each unique configuration would create a different universe, with different physical laws, and, crucially, a different value for the vacuum energy. This creates what physicists call the string theory landscape, a vast cosmic archipelago of possible universes. This leads directly to one of the most controversial and for some unsatisfying potential solutions, the anthropic principle. The argument goes like this. If there is a multiverse containing all these possible universes from the string theory landscape, then it's no surprise that we find ourselves living in a universe with a tiny vacuum energy. Why?
Because in universes with a large vacuum energy, the violent expansion would have prevented the formation of any structure. No galaxies, no stars, no planets, and therefore no physicists to measure the vacuum energy in the first place. We observe this finely tuned value because it's one of the very few values that allows for our existence. We are, in a sense, cosmic lottery winners. While this is a logically sound argument, many scientists find it deeply unsatisfying. It feels like giving up on finding a fundamental physical reason and instead resorting to a selection effect. It doesn't explain the value is what it is. The vacuum catastrophe remains the deepest, most humbling mystery in all of science. It's a constant reminder that despite our incredible progress, the universe is far stranger and more subtle than we can possibly imagine. Solving it won't just be about correcting a number. It will require a revolution in our understanding of space, time, and the very nature of existence.
The empty space around us is not a void, it's a puzzle box. And the physicist who finally unlocks it will redefine reality itself.